Now we move on to RL integrators and just go back through just what we did for the RC integrators. A series RL circuit in which the output voltage now is taken across the resistor is known as an RL integrator in terms of time response. Although only the response to a single pulse is discussed, it can be extended to repetitive pulses as described for the RC integrator. So as you know, each edge of an ideal pulse is considered to be instantaneous. Two basic rules for inductor behavior will aid in analyzing RL circuit responses to pulsed inputs. The first one, the inductor appears as an open to an instantaneous change in current and as a short, ideally to DC. And so if none of that makes sense to you, go back and look at your understanding on inductors, Lenz's law, and things of this nature to get your fundamentals back up on the behavior of inductors when they are in an excited state. The current in an inductor cannot change instantaneously. It can change only exponentially. So when we look at this, we can see first off here the output being taken across the resistor, and we have our inductor in the circuit and our pulse square wave generator. A series RL circuit in which the output voltage then taken across the resistor then is called an integrator in terms of the pulse response, and now it is an RL integrator. So as we look at this, it should all be familiar to you. I mean, it's the same explanation that we've seen before. When a pulse generator is connected to the input of the integrator and the voltage pulse goes from low to high, the inductor prevents a sudden change in current. Remember what happens here? The current is starting to flow. The field starts to expand. It starts, it starts to oppose. Go back again. Look at Lenz's law. It goes from low to high. The inductor prevents a sudden change in current. As a result, the inductor acts like an open, and all of the input voltage is across it in an instant that the rising pulse edge comes up. The situation that is indicated in 2033A, so we can see that here in this depiction as the pulse is generated from low to high. We have the exact thing happening on the positive side. It jumps up, and then the inductor starts doing its thing. After the rising edge, the current builds up, and the output voltage follows the current as it increases exponentially, as we can see here in B. So we're on the flat part of the curve here, the pulse width, and what's happening as the current now is pretty much just being choked off, and we see the exponential decline then in the voltage across the inductor. The current can reach a maximum then of V by R if the transient time is shorter than the pulse width. So in this case, our peak value, VP 10 volts, when the pulse goes from its high level down to its low level on the trailing edge of the pulse, then the pulse goes from a high level to a low level, and induced voltage with reverse polarity is created across the coil in an effort to keep the current equal to VP over R. The output voltage begins to decrease exponentially then, as we can see in C. So we can see when we've dissected the square wave, the pulse from the initial jump to the pulse width, and then as we make the transition from high to low, you can see here it immediately drops down to minus 10 volts, and then we have the exponential curve. The exact shape of the output depends on the inductor resistor relationship and the time constant as summarized in this figure. So if you take a look at this figure, you can see what's going on the input. You can see what happens with each of the time constants. Again, it follows what we've looked at before. In this case, we've got 5 tau greater than or equal to the pulse width, and then it goes down from there. So various relationships between the time constant and the pulse width are shown. You should note that the response of this RL circuit in terms of the shape of the output is identical to that of the RC integrator. The relationship of the inductor to the resistor time constant to the input pulse width has the same effect as the RC time constant that was shown in 20-4. For example, when the pulse width is less than 5 time constants, the output voltage will not reach its maximum possible value. Okay, so compare these to the RC integrator. We've got an example now. We want to determine the maximum output voltage for the RL integrator when a single pulse is applied as shown. The rheostat now is set so that the total resistance is 50 ohms. Okay, so just like we did with the RC with the rheostat, now we're going to do the RL. So we calculate the time constant. The time constant in this case, instead of being the product, it's the quotient, the inductor over the resistor, and we get 2 milliseconds as the time constant. Because the pulse width is 5 milliseconds, the inductor charges for 2.5 of tau. Use the exponential formula derived from equation 13.8 with an initial voltage at 0 and tau as L over R to calculate the voltage. So we look at our relationships here. V out maximum is equal to V final, and we multiply that times the difference, 1 minus E to the T over tau. And we get a value, in this case, of 22.9 volts. Again, pull out your calculator, run through that, verify it, and gain your skills here. A second example then, a pulse is applied to the RL integrator. Determine the complete wave shapes and the values for the current, the voltage across the resistor, and the inductor. So the time constant for this 5 millihenry 1.5 k ohm resistor is 3.33 microseconds. Since 5 times the time constant is 17.7 microseconds is less than the pulse width, well, the pulse width is 20 microseconds, the current will reach its maximum value and remain there until the end of the pulse. At the rising edge of the pulse, the current is 0. The voltage across the resistor then is 0, and the voltage across the inductor is 10 volts. The inductor initially appears as an open, so all of the input voltage appears across the inductor. During the pulse then, the current increases exponentially to V peak over R, which gives us 6.67 milliamps in 16.7 microseconds. The voltage across the resistor increases exponentially to 10 volts in that 16.7 microseconds, and the voltage across the inductor decreases exponentially to 0 in that 16.7 microseconds. At the falling edge of the pulse then, the current flow is 6.67 milliamps. The voltage across the resistor now is the full 10 volts, and across the inductor is minus 10. After the pulse, the current decreases exponentially to 0 in 16.7 microseconds. The voltage across the resistor decreases exponentially to 0 in that time frame, and across the inductor it increases exponentially to 0 in 16.7 microseconds. Okay, and you can see that in the waveforms here. So run through this step-by-step relationship, compare it to the waveforms as we see it develop here. Okay, another example. A 10-volt pulse with a width of 1 millisecond is applied to the RL integrator. Determine the voltage level that the output will reach during the pulse. If the source has an internal resistance of 30 ohms, how long will it take for the output to decay to 0? And then draw the waveforms. So again, first thing we do, calculate the time constant L over R, in this case L over R total. Then when we include the source resistance of 30 ohms, gives us 1 millisecond. Notice that in this case the pulse width is exactly equal to tau. Okay, 1 millisecond, 1 millisecond of pulse width. Thus the output across the resistor will reach approximately 63% of the full input amplitude in one time constant. Therefore, the output voltage gets to 6.3 at the end of the pulse. After the pulse is gone, the inductor discharges back to 30 ohms source resistance and the 470 ohm resistor. The output voltage then takes 5 time constants to completely decay to 0. 5 time constants, 1 millisecond, 5 milliseconds. So we can see that in the graph here, we jumped to 63% in 1 millisecond. We decay back down after 6 milliseconds, or 5 time constants. Okay, so we've got the same type of relationships here. Again, this is just a recap here. We got here the same thing here. This should be the previous one. Yep. So just a little exploded view on the slides. I've got a mixture of slides in here from presentations I've done before. Okay, so that's a recap. And again, there's our output. So you can take a look at those. They're a little easier to read. And in this case, the last example that we did, and you can see the graphical output. Okay, so that is our introduction to the RL integrators with a pulse input.